as well as the 2018 Breakthrough Prize in Fundamental Physics. In fact, the Breakthrough Prize launched Lyman's Hollywood career. And I have a couple slides to demonstrate that. Taylor, do you want to put those up there? Yeah, there we go. So there's, that's Lyman at the Breakthrough Prize ceremony with Miss America, Cara Munn from Bismarck, North Dakota. And here is the Breakthrough Prize team getting their award. Here's Lyman in his tux again. And here's who presented him with the award. That is none other than Mayim Bialik from the, Amy Farrah Fowler from the Big Bang Theory TV show. Very exciting. You get to hobnobbing. In fact, that wasn't the only Hollywood star. I thought I would play for you the actual award ceremony. Here it is.
The first of the Breakthrough Prize's $3 million gifts to our laureates. To present it, please welcome multiple Emmy nominee and neuroscientist Dr. Mayim Bialik and the president of Tech Incubator Y Combinator, Sam Altman.
As a neuroscientist who plays a neurobiologist on TV, it is a great honor to be here tonight among so many brilliant minds and to stand with Sam and help honor an ensemble cast that has earned the Breakthrough Prize in Fundamental Physics.
For me, the key to tech investing is having a long time horizon. If one day cities will be built from scratch by solar-powered robots, and they will, then I want to invest today. But the physicists we are honoring tonight are working with a time horizon that makes mine look kind of lame. These guys are really taking the long view. Plus, they're looking backward.
They built WMAP, a NASA mission that looked as far back in time as it's possible to see.
With WMAP, we see a picture of the universe as it was 300,000 years after the Big Bang.
We're looking at the universe's baby picture.
There's the baby universe. Okay, it is my great pleasure to introduce to you Lyman Page.
Okay. Uh-oh. Does that work? Yep. Great. Okay. Thank you, Vicki. Now I don't have to define all those terms. It's just start this here. It's great to be here, and thank you all for coming out. And what I want to do in the next 45 or so minutes is explain this picture and how we think about it and what it means in terms of just how we think about the universe. And it is a picture with some modifications, which so hopefully you'll appreciate in a little bit, of the birth of the universe. This is that's a picture of the whole sky. Okay, so you can imagine looking up at the sky, and here's the beach balls, this great demo here. Imagine looking up at the sky, we'll get to this red band later, looking out, and if you could look with microwave eyes, see microwaves in the sky, that's what you would see after you subtracted a constant term. And what you see there in temperature, sort of a heat map of the cosmos, from the bluest blue to the reddest red is about 400 millionths of a degree. And it is a picture of quantum fluctuations from the birth of the universe, and now blown up and writ large across the sky. Okay, so that's what, I will use the term CMB. It is the CMB, the cosmic microwave background. I'll lapse into saying that, so just stick that in your head. Okay, so let's, in order to understand this, I mean, some of the difficulties or the challenges of the cosmology are the distances and the scales we're talking about. So I want to start out. So the moon, right? The moon is, in the US, it's 240,000 miles away, right? You can drive a car there. And in Canada, it's 380,000 kilometers away. Right? You'll also drive a car there. But that, right, that's pretty nearby. That's 1 light second away. So the sun is 8 light minutes away. Right? So if the sun went out, and it would take us 8 light minutes to know, actually from both the electromagnetic signal, the light signal, and the gravitational signal. Okay, so the sun's 8 light minutes away. So, and we can go bigger. There's a picture of our galaxy there, and that was from the sort of the first great satellite, the COBE satellite, to measure the cosmic microwave background in exquisite position. That's the instrument on the satellite that didn't win a Nobel Prize for those guys, but it's an infrared picture of our galaxy. So it's like if you were in the outskirts of Montreal looking in, that towards the center of Montreal, and you could look in the infrared, you'd see it glowing, right? It's that sort of picture. And to set the scale, the center of that is about 25,000 light years away, right? So if someone were to send you a message from the center of our galaxy, and you wanted to send one back, that's a 50,000 year conversation, right? It's not a lot gets said, you know. How's the weather? You know, something like that, right? So that's the Milky Way, and to set the scale, there are for those of you who know scientific notation, that's easy, but for everyone else, right? That's 1 followed by 11 zeros. That's 100 billion. So there are 100 billion, roughly, stars in the Milky Way, in our galaxy. And to put that, and when I give you numbers like that, it's a factor of, you know, if you ask somebody who was really in this business, they'd say, no, it's 300 billion. So just this cosmology, right? So a lot of things we can still play around with factors of 3. But okay, so what is that? It's a huge number, right? So I just looked up this morning. So Jeff Bezos' net worth is 120 billion, right? So he has $1 for every star in the galaxy and then some. One way to think of it, if you're less monetarily oriented, it's the number of neurons in your brain is about 100 billion. Or if you have a sweet tooth, if you think of M&Ms, right? If you filled 50 cubic meters with M&Ms, that's about 100 billion M&Ms. Okay, so just sort of to set the scale. Okay, so those are all galaxies. This is this video, and this is just one of those. This is the movie from the Sloan Digital Sky Survey. We get it. Oh, it's playing. It's one of those movies, you know, late at night, you can turn off your lights and look at it. I still do. It's beautiful. Those guys are all galaxies, right? So, and you can see there's some clusters of them, but each one of those, you know, they all come in different shapes and sizes and things. But each one of those is about 100 billion stars. Okay? 100 billion will keep coming up, so remember that number, right? The one with 11 zeros after that. And this is moderately nearby. The edge of this survey is about 1.3 billion light years away to connect things, to connect to the center of the galaxy being 25,000 light years away. Okay, so there they are. That's and this is sort of getting out to cosmological scales, right? We can think of these galaxies like dust particles, if you will, right? So let's look at the Hubble Space Telescope again to get a picture. So here is an image from the Hubble Space Telescope looking out even deeper than that last one. And that's a really small region of sky. About 50 of those would fit in the full moon. Right? And you can go and carefully count up all the galaxies you see in there. And there are about 10,000 in that image. Okay? About 10,000 galaxies in that image, and then you just figure out the fraction of the full moon it is, and then you just multiply it up to cover the whole sky. And you get there are about 100 billion galaxies in, we say, the observable universe. So I'll come back to what that means. Okay, so there's about 100 billion stars in our galaxy and about 100 billion galaxies in the observable universe. And we look at them, these guys, they're all, as long as you get far enough away, they're moving away from us. Okay, they all are apparently moving away from us. So how do we think about that? And this is, I should say, everything I've shown you so far is just pure observation, right? These are just observations. They're counting. There's no interpretation. This too is an observation, right? The universe, everything's rushing away from us. And Hubble observed this first, or he more accurately was the one who put the data together to deduce this, and came up with Hubble's law. And it's a very special form of motion. And it says that the recessional velocity from us is proportional to the distance. So if it's twice as far away, apparently it's moving away twice as fast. 3 times as far, 3 times as fast. So that's what those arrows show. But now, so we're not that, we're special, especially up here, right? We're special, but in this picture, we're not that special, right? Imagine this goes on forever, and we'll come back to that forever in a little bit. Imagine it goes on forever, and instead of us sitting here, we jump to a neighbor. We were sitting instead on a neighboring galaxy. Well, in this picture, what you do is you just take that arrow, flip it over, and add it to all those arrows, and then subtract it from those arrows, and you see you get the exact same pattern here, right? So to someone over on this neighboring galaxy, to that person as well, it looks like all the galaxies are going away in proportion, rushing away in proportion to their distance. Okay, so no matter where you are in the universe, you see that same picture, and we'll work on that a little bit. But now, here's the thing I want to get across. If there's a concept that you should take away in thinking about the universe, it's that we should not think about the expansion of the universe as these galaxies, which are sort of markers coming out from a Big Bang, right? Don't do that. Okay, a much better way to think about it is think of space as the currency. That you are making space between galaxies that are like markers. Okay, you're making space between them. And if you make, and that's a hazy notion, it's hard to attach the definite physics to it, but keep that image in your head, that you can make space. And you see, if you imagine these dots just sitting there, and you're making space at the same rate everywhere, right? You're making space at the same rate, you would get this same pattern if you're making it at a constant rate, right? Because you're making it here, so he's moving away that far, but now, since you're making space there and making it there, this guy has to be moving twice as far because you've made twice as much space in that region. So we'll keep that picture in your head. Okay, so it's expanding. If it's expanding, we can extrapolate that back, right? So we extrapolate that back and we come up with an age. We say, roughly how long has it been expanding? We extrapolate back and we say that we'll get to this. It's about almost 14 billion years. It's been expanding. And so I just want to ignore, keep that time in mind. I want to just ignore the expansion for a minute. Now we know that the speed of light is finite. And so if you have 14 billion years and a finite speed of light, that sets a maximum size you have access to, right? And that is what we call the observable universe, to within a sort of a factor of 3. Okay? And that's that picture, and then the picture we have for the universe, if you could go anywhere instantaneously, okay? Go anywhere in the universe instantaneously, it would look everywhere like it does around us. Right? If you could go everywhere, every place, if you could go instantly, so forget about the speed of light, instantaneously transport anywhere, it would look just like it looks right around us, just like that picture from the Sloan Digital Sky Survey that I showed you. Okay? So that's ignoring the expansion. That's what it is. And when I say infinite there, with, that's, you know, the asterisks, exclamation points, all that, that is, what I mean there is, that's as far as we can tell by measurement. We have not been able to do any measurement that separates, that allows us to distinguish super, super, super huge finite universe from an infinite one. So that's what I mean by that statement. Okay. So now let's let's take the next step. So still ignoring the expansion. Okay, we still want to ignore the expansion because the speed of light is finite. Telescopes are like time machines, right? The further out right? These things are, 25,000 light years away. We saw the center of the galaxy 25,000 years ago. 1 billion light years away, we saw light that's taken 1 billion years to get here. The further out you look, the further back in time you look. Okay? So you're just looking back in time as you look out. And now you can sort of imagine this picture starting to come together. If you can look back in time all the way out to a remnant of the Big Bang, you're looking at, you can start to see that you're going to be looking at the early universe. Okay, so still, this is, again here, this is our Hubble patch, if you will, right? Further out, younger. Okay, and now, let's add the expansion and see where we are. What you can think of the expansion of the universe doing is that on its way to us, light from the edge of the universe, that Hubble patch, the light from the edge gets expanded. The wavelengths of light get expanded. Okay, and we'll get to it in a few slides, but at some point, the universe was much, much brighter back then, and the expansion has stretched all those wavelengths. And so it's now very cool radiation. It's cooled down to, instead of bright light, when you look at the sun, right? The sun is about 6,000 degrees, and it emits in the visible. You've taken that radiation and expanded all the wavelengths, so now it's 3 degrees and emits in the microwaves, in the millimeter waves. Okay, and then that first picture, this guy right here, these are variations in that temperature. Okay, so that's how we think about this radiation. And then let me sort of try to pull this all together in 2 more slides, and then I just want to take a breather and get some questions just to make sure we're all on the same page. Okay, so what do we have? We have some process early on, and inflation is the name for the most popular model. And there was this enormous expansion. Okay, this enormous expansion, and then we'll get to this process in a minute. We get, after these things, process is settled, and I'll show you what happened there, we get this so-called surface of last scattering, or decoupling. And that's when this radiation that comes to us, decoupled from everything else in the universe, and it travels almost unimpeded to us. So this is now, again, here we are, it's a WMAP satellite looking back, younger, this stuff, and then very soon before that, the say, inflation process. And it's these quantum fluctuations that have been expanded to enormous scales to make this picture. Okay, so then the light streams across the universe to us. Okay, let me show just one more picture for how that works. I think. There we go. From very early on, the universe expands and cools from its really fiery beginning. But, you know, it expands and its temperature drops, it expands, and the temperature drops. And it's really hot early on, and it's so hot that electrons cannot attach to protons to make hydrogen. There's so much light, they just get ripped apart. Finally, it gets cool enough, and the temperature that it is when this happens is about half the temperature of the sun. All of a sudden, you can form hydrogen atoms. And when you can form hydrogen atoms, the radiation can go right through. It doesn't interact anymore when those electrons are bound up on the protons, they don't scatter radiation. And so then the universe becomes transparent. And so that's what's going on in this picture right here. Hot, early plasma, and then all of a sudden the universe becomes transparent. The radiation decouples from the matter. The matter then goes on to form all this cool stuff, right? All the structure in the universe, us, stars, galaxies, everything, all happens through here. And where this happens, these spots are sort of seeded by these quantum fluctuations that are also manifest as these hot and cold spots in the microwave background. And I'll get back to how to think about those in a minute. But before doing that, just on this conceptual picture, let me just stop for a minute and see if you have questions about it, just to make sure. So if someone has a question, I'm sure others will. Anybody? I have a question for you, Ben. Anyone have a question? Oh, yes, good. Way back, things have definitely on this picture, or on this picture. Just think this is an artist's rendition, right? Let's go way back, and there weren't any galaxies, right? Yeah. Yes, exactly. Well, it tries to, but yeah, right. And I should say it tries to with this outline is like the expansion of space. Okay, that's what that's. It's an absolute artist's conception. But absolutely they were, absolutely. And it's like if you took those 50 cubic meters of M&Ms and expanded it into the future, right? You'd have all the same M&Ms, they would just be further apart. If you rolled it back, they'd all be closer together. Okay, so then my question for you is what would somebody on the edge of the observable universe right now, looking back where we are, right here, what would they see? No, if you were instantaneously transported to the edge of the observable universe and you look back to where we are, what would you see? Same thing being, you would see the microwave background. You would be in the center of the sphere of the cosmic microwave background. Right? So when we think about the Big Bang taking place, it happened everywhere. Right here. It was enormously hot and dense. Okay? And the universe expanded. And the universe just say, God, we don't care about the expansion because we're sitting here. It was full of radiation. It just sat here and cooled. Hydrogen formed then. Then hydrogen formed, and then it came together. The radiation cooled. The radiation, it's all gone. All the radiation that was here is now 13 billion, 14 billion light years away, right? So everything happened here. Every place in the universe, the same thing happens. Okay, so the Big Bang happens everywhere. And when we say it's infinite, we talk about it being infinite, it's that we just, again, we can't distinguish it through measurements. As far as we can tell, that pattern goes on forever. It's got to break down at some point, but that's what we should think about it. So let me try to pull this, again, putting this picture of formation, galaxy formation, structure formation, and the microwave background together. This is a movie, if I can get it to go here, and you can hear it, that, let's see, oh, there it is. This is Rachmaninoff in the background. So this is a summer project from a student. So there's the Milky Way, and you'll see where we are in a minute. Oh, good. There should be a little label coming up in a minute. There we go, home. Okay, that's roughly where we are in the galaxy. And then those guys there are just a small sampling of the sky, and those guys each represent a cluster. And you can see how far away they are. Those are each clusters of galaxies. So those guys are roughly 1,000 galaxies. Okay? And we see them, and this is and so now we're zooming out 5 million light years, 10 million light years, 50, 100 million. There, there, 1 billion. That's where that first video ended. And now these are just galaxies all over the sky. Okay. And now we'll zoom out even further. Out here. And you will see the beach ball. There. Okay, so the picture is then that space was full of these quantum fluctuations. These hot and cold spots are from the radiation responding to those fluctuations we'll get to in a minute. And then structure formed, and the timeline is rolled out from where we are, say back to there, whichever way you want to think about it. And because of the speed of light, that's all we have access to. Okay? Who knows what's going on out here? Okay, so that's the conceptual picture. Okay, good. So how do we measure this? So here is, so I used to be able to show this. So, so how do we measure the microwave background? And I say you've all detected the CMB, but that's really an age-dependent statement, right? Because you have to have, if you have a TV and an antenna, and you tune it to an inactive channel, right? It doesn't work with cable, right? So or whatever, all these, network TV things. Anyway, right? You have to have an antenna, and the radiation, right? This radiation that's left over is 3 Kelvin, okay? That's 3 degrees above absolute zero. Room temperature is in those units 300 Kelvin, 300 degrees. So roughly 1% of that fuzz there on your TV is from radiation left over from the Big Bang. And what we do is in all these instruments that we build to measure this, we just build various versions of very fancy TV receivers and just point them around the sky, okay? And we measure the change in the amount of fuzz as we point at different places. That's what we do, okay? And then we have to do it, we do it carefully, obviously, and all sorts of things like that. So, so here are the, these all sky measurements come from these 2 satellites. This is WMAP that Vicki mentioned. This is the Planck satellite, which is the most recent. Actually, the map I showed you in that last video comes from the Planck satellite, and this has huge participation from Canada. I mean, a lot of thinking, a lot of the analysis from this came out of the University of Toronto. The other things, the other instruments that we use are here at higher resolutions. So this is sort of where the state of the art comes from. There's a telescope at the South Pole. Matt Dobbs and company are intimately involved in that. There's one colleagues and I are involved with here in Chile, and there's another one Matt and colleagues are involved with also in Chile. Colleagues at UBC are involved with that one, and Toronto involved with that one. So there's huge Canadian participation in this whole thing, and it's and I'll come back to a little bit more of that later. So we're all making these measurements, and why do we get to go to these great places? It's because water interferes with what we try to measure. It's just water vapor, so we want to get away from water vapor. So we go to really dry, cold places like the South Pole, or really high places like in Chile. Those telescopes are at 5,200 meters in Chile. So what do we see? This is a map of the sky going back to WMAP. So this is it. This is closer to what we actually measure. And again, that's the full sky wrapped around, these temperature variations. That's just the galaxy. So if you remember back to that quote, that Derby picture, seeing the galaxy, we also see it with light that's a half a centimeter of wavelength. So that's what we measure. Let's zoom in on a part of that so you can see that's just below the galaxy. And then zoom in a little more. So this is I want to talk about what it is we actually see here. So if you were to look at that picture, it looks fairly random, right? But there's a characteristic size to those blue and red spots, those hot and cold spots. So if you looked at that, what would you guess characteristically? Degree-ish. I mean, it's about a degree. These spots are, there's some big ones, there's some tiny ones. A couple of degree, right? Those are the spots. So what are those? Those are the hot and cold spots in the sky. That's the signal we're after here. Okay. So what is it? What do those come from? So how do we get those hot and cold spots? Well, that something like inflation laid out through quantum fluctuations a gravitational landscape. Right? There are truly these quantum fluctuations that got blown up by this enormous early expansion and were manifest as variations in the strength of gravity. And the radiation early on and the matter combined into a plasma falls into these potential wells. You can think of it like a fog falling into the valleys of a mountain range. Okay? And so remember that decoupling time. There's that decoupling time about 380,000 years. All of a sudden, then the radiation was set free. So the amount the plasma can move, here, the spot size, is just the speed of the plasma times the age of the universe at decoupling. Okay? So that's it. You just take the speed, and it turns out you can compute the speed, and you can compute the speed because this is just a plasma at half the temperature of the sun. This is simple physics. It turns out the speed is really close to the speed of light over the square root of 3. Okay? You can just compute that. Okay? So all of a sudden, we have a spot size. Now, what we do is we go up with these instruments, the satellite, and we measure that spot size. We measure both hot and cold. And this spot size, and this is from the Planck satellite. This is taking all the hot spots in the map and stacking them up on each other. And we can measure that size super accurately. Right? I mean, this is just one of the best measured numbers in cosmology. So we've been able to compute the size of it, right? Because it's just the speed of a plasma times the age of the universe at decoupling, all computable with straightforward physics. And now we measure the angular size. So we have a distance, we have an angle. So we have a size, we have an angle. So we have a distance, right? Okay, because now we can tell how far away that surface is. Before I show you what we do with it, let me just give you this other picture to put the sort of in perspective. So there's that same spot size here. Here is the North Celestial Pole, is right in the middle there. That's the same size as the moon. So these spot sizes are about the same size as the moon. Everyone knows you don't see the moon next to the North Celestial Pole, right? So that's just to give you an image. Next time you look up at the North Pole, North Celestial Pole, just think of this happening there. That's what you would see right there with microwave eyes. Okay, so we have that spot size, that standard yardstick. We have the angle, so we know the distance to the edge of the observable universe. Right? Knowing the distance and the speed of light, we can deduce the age of the universe. And it really, this is obviously a simplified picture, but it really falls along these lines. We can then deduce the age, and it's 13.8 billion years. So remember, so two numbers, right? Measure 13.8 and remember 100 billion. Okay, so we know the universe is 13.8. And we know a lot more than that. So this is the plot that I'll show. So this is, and what I want to show you is this is, although I've been a little loose with factors of 3 in places, this is now super precise science. Okay, like you saw that number, that 0.6, almost 0.6 degrees. This is a plot. Just look on the top. There's angular scale. Right? Larger is to your left, larger angular scale, so that's 90 degrees. That is that degree scale, first peak. Don't worry about the difference between 0.6 and that 1 degree. It's just the convention. That's where all the fluctuation power was in there, right? Everything was jumping around at these scales of sort of a degree. And not only do we see that plasma compression, but we can see all sorts of secondary effects in here. And I'll show you an updated plot of this in a while, but here's what you should take away. Those are real data with real error bars from the sky, and the red is the model of the universe. And that model just has 6 parameters. And what it means and why we're learning about the heavens so accurately is we can make those measurements super accurately, way more accurate than this shown in this plot here, and fit models and really zero in on the model of the universe. And that's what we've been able to do. And so and not just WMAP, the whole field. This is what we've been able to do. It's just pretty amazing that it's pretty amazing we can do this. So what model do we get? So here it is. It has 6 parameters here. Here's the pie chart. Because we see that the universe is geometrically flat, that means they have to come back to that. It has to sum to 1, but it's made up of this. It's roughly, so these are numbers we now know to sort of percent, but I've rounded them off here just so you could keep them in your head. Roughly, the atoms, the stuff of which we're made, is only 5% of the universe. Right? Not much. We know there has to be more matter there that's not atoms. It's called cold dark matter. Not only is it not atoms, it's dark because it doesn't interact with light, and it's cold because it's not moving that fast. And I won't go into the details, but I'll tell you, it comes because we can measure that peak right there with enormous accuracy. And then this other thing, this lambda, this cosmological constant, or dark energy. So this is dark matter, dark energy, and then this is the stuff we know, right? So that's what we have. Oopsie daisy. Is that me or it or, oh good. All right. Dark something, dark light, okay. Okay, so I mean this is an amazingly accurate model, right? You can see because that red curve fits the data so well. But it really raises a lot of questions. This dark energy, right, has no foundation in any fundamental physics theory, right? Any fundamental model of physics. It is almost like it's as though the vacuum has an energy associated with it that drives the universe apart. That's why I sort of felt free about making space, right? It's like the vacuum has an energy density with it that's driving the universe apart. Okay, and most feel that this dark energy term is not, it's not really something new. It's that there's obviously something new. It's that something really deep we're not understanding about fundamental physics. There's just some piece of the theory that we're really missing. And lastly, what's this dark matter? People have been looking for this for decades, and no one's been able to find it. When a huge effort is taking place right now in Snow Lab in Sudbury. Everyone's looking for it. No one can find it. What is it? We know it has to be there because we see its set gravitational signature, not only in the microwave background, but in lots of other things. Okay, so what's the model? This is sort of the abbreviated standard model of cosmology. So at some very early time, a quantum field impressed on the universe a gravitational landscape. And this is what we measure. When we say we observe the birth of the universe, that's the picture we have in mind. The matter fell into those gravitational wells, that gravitational landscape, and to form all the structure in the universe. But the matter, only 1/6 of it is familiar to us, right? Which is so great to have these huge open questions, even though we know what we don't know very precisely. The dynamics of the universe is now driven not so much by matter. Matter is going to be irrelevant as the universe expands more. We are increasingly become cosmological constant dominated. You look at the pie chart. As time goes on, the matter just becomes tiny little slices. It all becomes the dark energy term. Okay, so that's the way we're thinking about it. I want to finish up here with a frontier, so there are all these questions, right? What are these elements? How do they fit into theory? What is the dark matter? So it's an incredibly successful model. There's some observations that might be in slight tension with it, but those are being investigated right now. But there are some real frontiers, and I just want to point out one of them because it connects to a cool measurement that was done a couple of years ago. And there are a bunch of elements. I mean, we now know this radiation so well that we can search for the characteristics of these hot and cold spots in conjunction with galaxies to determine the mass of neutrinos. Frontiers we're after. I want to finish up though with another one that's even cooler, and that is we are searching for gravitational waves from the birth of the universe. And the question is, are they there at measurable levels? So so what is a gravitational wave? First off, it's a strain that propagates through space. So for a gravitational wave, if it's propagating that way, and they propagate at the speed of light, what it's going to do is squeeze space this way, expand it this way, squeeze it that way, expand it that way, as you go on. And when you say squeeze, it's just a strain. Okay, so here's 20 centimeters, right? So you measure it in terms of strain, gravitational waves. This is 20 centimeters. If this gravitational wave came by here and squeezed this 1 centimeter, we'd say the strain is 5%. Okay? That's the strain. LIGO, the Laser Interferometric Gravitational Wave Observatory, just a few years ago, discovered 2 in-spiraling black holes. And I should say these are things very close to both the microwave search and this are very close to things going on right here in McGill. These black holes coalesced and they emitted gravitational waves. They sent these strains out through space, but the strain is one with 21 zeros in front of it. Okay, tiny, not 5%. That. Okay. To give you an idea, that strain corresponds to the difference of about 1 human hair between us and the closest star system. Okay? Absolutely tiny. That's 4.4 light years away. A human, and what's so neat is the people who designed this realized they could make a measurement that precise on Earth, right? Pretty mind-blowing. Okay, these waves from this in-spiraling black hole have a wavelength, oscillation period of about 100 cycles per second. What we're searching for, and Matt and colleagues especially involved in this, what we're searching for are these gravitational waves produced from the extraordinary densities in the birth of the universe. Those same quantum phenomena that gave rise to that static gravitational landscape also could give rise to gravitational waves. And these strains, according to some of the models, are as large as a part in 100,000. So huge, right, by LIGO standards. But their period are like 100 cycles in the age of the universe, right? So they're static to us. And we can think of that strain with this beach ball example of they are deforming the size of the observable universe by a part in 100,000. Okay? And we are looking at the microwave background to look for that strain. We're looking at the spots, and we're looking at a particular feature of the spots. There, it's this mind-blowing connection. If we found them, we're looking for a particular element of the spots. And let me just show you what that is. We're well past looking at the temperature fluctuations, and we're now looking at the polarization. So this radiation that you see, if you had microwave eyes, if you had microwave polarized sunglasses, right? I guess you wouldn't have sun there, but right, microwave polarized glasses, and you held them up to the sky, and you turn them, the pattern would be different. Okay, that radiation left over from the Big Bang is polarized, and that's been measured really well. To give you, to go back to that first slide, the temperature variations, I said from the bluest blue to the reddest red was 400 millionths of a degree. So if you sort of the average, if you take the average fluctuations, 100 millionths of a degree. The polarization, the size of the polarization of those same units is 6.4 millionths of a degree. The gravitational wave signal in here, we now know from measurements has to be less than 100 billionths of a degree. But we're confident that we can go and measure that at least a factor of 10 better. So it's still really, this field is incredibly exciting, and we're still learning, tackling them. Here, this is a little more technical, but I want to juxtapose that earlier slide, which is probably 10 to 15 years ago, 10 years old, to what's just happened in the past few years to give you an idea of the excitement. Not only, and this is that's Dobbs and Company, and they're all Canadians, all represented all over this plot here. There's the temperature anisotropy I showed you for. This is the variance versus, I didn't put the angular scale on here. Now the polarization signal has been measured incredibly well. And this other form of polarization signal has been measured incredibly well. And we're looking, those gravitational waves are here. They're going to end up down in this spot. You can still see the error bars are large. But to give you faith in that we really know the cosmological model, the line through there, that's based on a model from the measurement. That line that goes through all those points is the same model that was predicted before any of these data were taken. The same line that goes through there. Same model, all based on these measurements. So you can see we're measuring the fluctuation power in the sky over 5 orders of magnitude, and this whole picture hangs together. So it's sort of in this new era of very precise observations of the cosmos. So let me end there with so many of friends and colleagues, the Canadian CMB community. There will be a few additions soon to come, and thank you. Sure. Sorry. Of course. It's what yes. What is the James Webb Space Telescope, soon to be launched, bring us? And it is, for those who don't know, this is this huge new NASA project, NASA telescope, and gets launched of order a year, something like that. And it will be like the Hubble Space Telescope, but observe infrared radiation. And what it's going to do is be able to, so the Hubble will stop something here, it will even be able to look back further into this picture. It will do many, that's one of many things, search for planets, but in terms of cosmology, it will be able to look back and look younger, okay, in galaxies. Simple way to answer it. Yeah. It came along with it right then. And I should say, when we say that 13.8 billion years, that's for, if the universe is cyclic and we don't know that it's not, it could be, that would just be for this phase of it. But all the radiation came then. Pardon me? Yes, no, it's the stuff you can imagine. If you were a mathematician, you would work with universes that had nothing in them, right? It's just a coordinate system, and it has nothing in it, right? And it so happens, in some of these, in some of these models. Well, I'm not a mathematician, right? Of course. And even other models of the universe have whole different forces going on. So they might not have atoms in them. They wouldn't have the dark matter. These are universes that we have no access to. So I've sort of not wanted to focus on things we can really measure. I don't know if that helps. It all comes together though in our universe. So, great question. So here's, on our lifetimes, yes, okay? But, so this is sitting out, this is sitting in this is like an ice cream scoop out of this larger space, right, that we don't yet have access to. So what happens to this surface as the universe expands, right? It grows. This grows out. So what is say a red spot here? That's where the plasma contracted and the plasma rushed into a well and got hotter in that region. But this distance to which we can look will grow, and so it will start to leave that region and run into other ones. And so you can actually, if you wait long enough, you will see this pattern change. And you can actually, we once wrote a paper on this. You can if you do precise measurement now and a precise measurement in 100 years from now, you can watch the expansion of the universe in real time. If 100 years is real time to you, but it will change. Yeah, I hope that it's great. Yeah. So remember, think about it. So think, when you think about space, just think about, we don't want to, like, explosions. We hate the word explosion in cosmology, right? Because think about just space being much, much more compact then. Infinite, always, as far as we know, always has been, always was. Just way, 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 way more dense. Okay? Here's another spatial example. Imagine a raisin bread, okay? All the raisins are galaxies, and now imagine you start as a dough, and you put it in a huge, huge, huge oven, right? And it's just expanding everywhere. We're in the middle of it. If it's so big that you can't see the edge of the raisin bread, that's what it's like. Okay, it's just so big we have no access to it because, right? But if you go back, if you keep pushing the dough together early on, you just keep, put in the vise, you do all that stuff. You just get it more and more compact. But that's all we know. Physics breaks down at the very smallest scales. We just don't have the physics to describe it. And I should mention, at Waterloo, right, a whole bunch of work is going into thinking about how to, like, what sort of universes can you get by playing with those very, very, very early times? Trying to piece that all together. But you just think about it in space. Think about taking away, you just take away space, you take away space, you take away space, all the way back. Yes, because I'm giving a colloquium on Friday. But it's because when we do these measurements, we do them at WMAP was 5 frequencies. With the Planck satellite, it adds another 8 frequencies, and we do them as a function of frequency. And it turns out it's because this radiation has a called a black body spectrum. It has a very precise spectral signature, and we can separate that signature from emission from the galaxy. And we can do that accurately, and we can do it we can do it as a function of where we are in the sky to check it. And we can do things like make sure the subtraction is good over here and good over here. And if you looked in V-band, half a centimeter radiation is the cleanest. That's why I showed that. But you can, and that's this. If you just lop that off about there, that you could make all those plots with just the top, and there's no galactic contamination. And stars are too small. You got it. And it's 75%, 25%, 5% in rough numbers, right? And the dark matter is what, and because there's a twist or just a little bit more information about what I said, right? If you have these gravitational potential wells, if you try to get atoms to form in them, they scatter off the light, and that slows them down. But the dark matter, since it's dark and doesn't interact with the light, just falls in and sort of speeds up the process, if you will. Yes, but it's more. It's in the universe. It's more that the other forces here. Oh, that's probably me. Here we go. I think I did that. On purpose. Okay. The other forces. The other forces are so large that we can't possibly tell it. Right? I mean, just the chemist, geology, local gravity, all completely overwhelm it. And it's true for our solar system and true for our galaxy. We will never see the galaxy being torn apart. Good. Thank you. Good.